Hey guys, we're going to do a second example problem with single displacement net ionic reactions and half reactions. So I have another example problem here. It's iron plus copper 2 chloride. And so the first thing we have to do is predict our products. Now iron is also a transition metal where they have different oxidation states. So we don't clearly know which charge to use unless there's some other piece of information in the AP problem. So I want to specifically do something here to show you guys how the charges balance and things like that. So I'm going to choose iron 3. So when I combine with copper, I'm going to combine with chlorine because that's the negatively charged thing and iron is positively charged. I'm going to make an iron 3 chloride. So that's going to look like this, FeCl3. Then my other product is going to be copper kicked out by itself, so plus Cu. Now, the next thing we have to do is balance this reaction. So I see that there's 3 chlorines here and 2 chlorines here. To balance that, I'm going to put a 3 in front of both the coppers and a 2 in front of both of the irons. What that's going to do is give me 6 chlorines on both sides, 3 coppers on both sides, and 2 irons on both sides. So I have a balanced reaction. After I balance my reaction, I'm then going to assign solubility rules. Since iron is by itself, it's just a solid. Copper 2 chloride, according to solubility rules, is aqueous. Iron 3 chloride, according to solubility rules, is aqueous. And then copper by itself is a solid. So now I figure out my spectator ions. Chlorine here, or the chloride ion technically, is aqueous on both sides. So we're going to cross that out. Now we bring everything down. Remember, if it's a solid, you let it stay the way it is. But if it's an aqueous solution, then we have to represent it as its ion. So iron gets brought down like so. Copper gets brought down, but I have to represent it as its charge because it's aqueous. Iron gets brought down. I have to represent it as its charge because it's aqueous. And copper is left alone because it's a solid. So this is my net ionic equation. Now let's talk about our oxidation and reduction half reactions. So I have to figure out the species that is oxidized. So remember, oxidized is losing electrons. So what happens to the oxidation states? The oxidation states get more positive. So the thing that is getting more positive as the reaction proceeds is iron, because it's going from a 0 oxidation state to a 3+ oxidation state. So we are going to write that down. So I'm going to have iron solid yields Fe3+. Now notice how I am not using my coefficients when I write my half reaction. You do not have to include the coefficients when you write the half reaction, because what's going to happen is it's going to reduce completely. And so iron goes to iron 3+. I have to state how many electrons it's changing by, which is 3. So there's going to be 3 electrons there. And this is my oxidized half reaction. Now I have to write my reduced half reaction. So remember, reduction is gaining electrons. So what happens to the oxidation state? If I'm gaining electrons, my oxidation state is getting more negative. So that is what this copper is doing, because it's going from a 2+ to a 0 charge. Now let's write that down. Cu 2+ yields Cu. And how many electrons is being transferred there? There are 2 electrons. Again, I'm not going to include these coefficients because that will be reduced at the very end, and I'll show you what that means in just a second. So 2+, I have to balance out my charges, so my 2 electrons will look like this. So let me show you, just so I'm not confusing you, what would it look like if I am not neglecting these coefficients here. So what I would do for this first one with iron is I would bring down the 2Fe. I would bring down the 2Fe3 plus, but instead of 3 electrons it's changing by, 2 times 3 plus is equal to 6 plus. So the oxidation state for the iron totally is 6 plus. So I'm not changing by 3 electrons, I'm actually changing by 6 electrons. Now, if that's the case, I would have to put a 6 right here. Now, what do you notice about this reaction? 2, 2, and 6 all reduce to 1, 1, and 3. And so that's why it's okay to simplify by neglecting those coefficients when you're writing those half reactions. Same idea down here. My copper 2 plus, let's bring down the 3 with it. Let's bring down that 3 with him. So he will not be changing by 2 electrons, he will be reduced by 6 electrons. So you see how this right here also reduces to 1, 2, and 1. And so that is why it is okay to be able to leave out those coefficients when you're writing down the half reactions. So I hope this is helpful. Let me know if you have any questions.